Welcome to the third part of the OWL class. Here we will be looking at OWL class axioms after we've looked into the OWL properties. Defining OWL classes is relatively straightforward. There's always one type of class you can define. Every class you create in OWL is of type OWL class. Our class is a transitive, has a transitive relationship with RDFS class. This means recall that OWL is more expressive than RDFS. So for every class that you are defining as OWL class, you are also automatically defining that this class is of type RDFS class. There is a special there is a special class, which is OWL thing. This includes all individuals and all classes in an ontology. This means that for every class that you declare, this will be automatically defined as a subclass of OWL thing. Similarly, this is for individuals or instances is the same thing. Every individual in OWL is declared as type named individual. By transitivity, every named individual is also an OWL thing. Additionally, there is a special term opposed to OWL thing, which is OWL nothing. OWL nothing is an empty set. So there is no individual and no class that can be subclass of or type of OWL nothing. OWL nothing is only declared as only used to indicate inconsistency, to make sure that your ontology is correct, and every class that is being created is automatically disjoint with OWL nothing. Looking into the class axioms, they are mostly, you need to think of class axioms mostly as set operations you can do over OWL classes. We start with equivalence and complementarity. Equivalent classes contain the same individuals and have the same definition. Most of the time you use equivalence between classes. So the term you use is OWL equivalent class when you have two classes in two different datasets. Imagine that you have the Wikipedia on one side and you have the class Dutch painters, and then you have the Rijksmuseum dataset on the other side that also represents Dutch painters. Then you can declare these two classes as being equivalent, and there will be triples that will be inferred for all the instances, so all the elements that belong to these classes. So if we declare that Van Gogh was of type Dutch painter, and then we declare that A is equivalent to B, then Van Gogh will also be declared of being a Dutch painter into a different data set. So the two classes are absolutely the same, and they contain the same individuals. The complementarity of the class is the opposite. So the complement of a class contains all the individuals that are not in a class. This means that if I declare that A belongs to the class A, recall that lowercase is used for instances and uppercase is used for classes, then I'm declaring that A does not belong to any other class. Notice that the complement of a class that you declare is everything that in our thing that the class is not. So if you say that that the class female and the class male are complementary, then you're basically saying that all females are not males. In this sense, you can see an example here. We declare that B is the complement of A, as in the picture. B, the instance B belongs to B, the instance A belongs to A. And we say the instance B is of type OWL thing. the reasoner will therefore automatically infer that B belongs to the class B and not to the class A. So the complement of a class is all of our thing that the class is not. Another example is living human complement of a dead human. A dead person cannot belong to the living human class. Disjointness allows to represent classes that do not contain the same individuals. The complement and disjointness allow us to infer that individuals are actually different. So if you say that A disjoint with B, and then A is of type A, and you say B is of type A and B, so your B instance appears here, the reasoner will declare this is information that is inconsistent. That can, according to the disjoint with, that cannot be an instance that belongs to the class A that also belongs to the class B. The typical example is man and woman. If you declare that man is disjoint with woman, and that X is of RDF type man and Y is of RDF type woman, then the reasoner will infer that X and Y are different from each other. Recall the use of different from, which is a special keyword that the reasoner uses to distinguish between individuals. The union and disjoint unions are concepts that allow you to combine classes among each other. If we declare that a class is the union of two other classes, it means that the instance of that class will be both belonging to all the classes which belong to the union. A good example in this case is girl is the union of female and a woman. So for every instance being declared as every individual being declared as instance of the girl class, we can infer that the instance will automatically be also of type female and also of type woman. So here we have girl is a union of female and woman, and then ace is of type female, ace is of type woman. Therefore, ace is also we can infer that A is also of type girl. Disjoint union is the opposite. Is a union of mutually disjoint classes. So the elements, the instances of one class and the instances of another class, but they cannot belong together. So we can declare that a child, she, is the disjoint union of a boy or a girl. But for every instance that we define, so a given child A cannot be both a boy and a girl. This is declared as being inconsistent. Finally, we have intersection. Intersection contains the individuals that can belong to both classes. So this is the opposite of the disjoint union. So C is in the intersection of A and B, and then we declare as A of type A and A of type B, then A can also be inferred as being of type C. An additional operation that we can do is to enumerate the members of a class. The members of a class are saying members or saying individuals or saying instances is always the same thing. So the members are the instances of a given class. There might be cases where you want to declare in your ontology who are the individuals that belong to a certain class. If I'm describing a Formula 1 word, for example, I might want to specify who are all the Formula 1 pilots. So A is a Formula 1 pilot. And then I say a Formula 1 pilot is one of the following members. And then it can say Max Verstappen or Lewis Hamilton and so on and so forth. if you declare that a given member is of type owl thing, this will be automatically inferred as being of type Formula 1. Another example is gender or sex, where you might want to declare that you can be either male or female. In these days, we might also want to expand the enumeration with less binary members.